Audio Jungle. Audio Jungle.
Right. Now we have the static pressure rise in rotor, okay, or the static pressure rise by rotor in axial flow compressor. So we have static pressure rise by rotor in FC axial flow compressor. This is very important. Till now we had calculated that pressure rise in stage we have calculated, but individual static pressure rise by rotor, that amount we are going to calculate here. Okay, so you know that in my previous lecture I had explained that in fact total enthalpy also across the rotor is what constant, but it's a relative enthalpy, and total enthalpy across the stator will be constant, but it's a absolute enthalpy. Okay, always remember this big difference. So now we have, this is the velocity triangle, this is the velocity triangle. Okay, all right, alpha 1, beta 1, this is what C1, this is W1, this is WT1, CT1, and this is what CA. And this is the rotor plate. Okay, and for this rotor plate, this is the velocity triangle. This is what C2, this is what W2, beta 2, alpha 2, CT2, and this is WT2. All right. Now, if you are going to check, this is what stage. This is the one stage 1, 2, 3, and this was rotor and this was stator. All right, and across this we had calculated, for the stage we had calculated P03 by P01, and that was RP, pressure ratio, that also we had done. I'm saying you like what is the pressure, static pressure rise by this rotor, and this rotor is nothing but delta P. This is the static pressure rise by the rotor, and this value till now they had not asked question based on this, but anytime they can ask, because this is the very nice derivation actually and very important data. No? So what is the static pressure rise by rotor? So obviously here it is nothing but, check this value, this static pressure rise here, it is nothing but between 1 to 2, so it is, you can say P2 minus P1. This value you need to calculate. Okay, this value you need to calculate. This is very important, no? So one thing you know very well, in my previous lecture if you see, then I had given two things, total enthalpy and total pressure across the rotor will be constant, but it will be relative value. Okay, so I can say P01 total pressure, and this will be relative equal to total pressure. Okay, it is relative across the rotor. This is the constant value. Okay, so across rotor we can write here, across rotor, this is the data. And similarly, if you remember, I had given total enthalpy also, it was relative only and it is constant. Okay. Now we are going to follow this because we are interested in calculation of the static pressure rise in rotor. So we'll take relative pressure across the rotor, that will be constant, means P naught 1 relative is equal to P naught 2 relative. Alright, that we are going to do here. Now if you check, P naught 1 relative is equal to P naught 2 relative. So we know the total pressure is the stagnation pressure, and this is nothing but static pressure plus dynamic pressure. So what is the static pressure for P naught 1? Static pressure at point 1 will be P1. This is the static pressure plus dynamic pressure. What is the dynamic pressure formula? It is half rho V square. So half rho, and what is the velocity? Because it's a rotor, so across the rotor relative velocity omega 1 will be there. Similarly, static pressure at point 2 it is P2, and dynamic velocity dynamic pressure will be half rho, and velocity will be relative velocity. I told you, I explained nicely like why relative velocity will be recognized by the rotor. That I had discussed, so no matter, now I have written directly here. Now what will be the P2 minus P1? You can write P2 minus P1 will be what? Delta P, and definitely it will be the static value, and obviously it is for the rotor, but this change of pressure is what is static only. So what is P2 minus P1? You can check half rho, and this formula W1 minus W1 square minus W2 square. Okay. Now from this triangle, why I have drawn this triangle, you can check what is the formula of cos beta 1. So cos beta 1 is nothing but I'm interested in this what you can say W1. So CA is constant, so what value you can take? Base and hypotenuse. It's a tan, sorry, it's a tan. It's a tan, no? Because base and hypotenuse you need to take, not perpendicular. So what will be the tan beta 1? It is CA divided by W1. So we can get W1, which is nothing but CA tan, which is nothing but cot, I think, no? No, what I'm saying. Yes, wait.
Tan beta 1 will.
So sorry. So now this will correct. We will correct this. So what we'll get here? Check. We have cos beta 1. It is CA divided by W1. So we have W1 is equal to CA sec beta 1. Similarly, we can write W2. It is CA sec beta 2. This two value we have to keep here. No? So now this is P2 minus P1, and this value is what? Delta P. Okay. And this value is what? Half rho, and this W1 is nothing but CA square sec square beta 1 minus CA square sec square beta 2. Now if you check, this value is nothing but half rho CA square, and this is nothing but sec square beta 1 will be, if you check this formulation, so I think it will be 1 plus tan square beta 1 sec square beta, right? So 1 cancel out, both places we have, so plus minus it will be cancel out. So ultimately if you check directly, I am going to write tan square beta 1 minus tan square beta 2. Okay, and this is nothing but delta P. This is very important formula. This is very important. I was trying to give direct formula, but I thought it will take very less time to derive this. So ultimately this is the formula, and it's very powerful. Okay, so as I told you, they have not asked the static pressure rise in rotor, but anytime they can ask beta 1 beta 2 will be available and they can ask questions, so you need to answer. Remember, this is the static pressurized by rotor, not for stage. For the stage I had given the formula, what is the pressure ratio across the stage, and obviously pressure ratio if you get, then obviously you change of the pressure, you will get that, not a issue. Check extension of this. Now you can extend this formula. So what you will have, you got delta P static pressure rise by rotor. So this formula you got 1 by 2 Ca square tan square beta 1 minus tan beta 2, and here we have rho value, half rho Ca square. So we can write this half rho Ca square. This formula you got, you can write tan beta 1 minus tan beta 2 and tan beta 1 plus tan beta 2. So you know degree of reaction. What is the degree of reaction? Ca by 2u. Ca by 2u, you got tan beta 1 plus tan beta 2. What I remember, it was Ca by 2u tan beta 1 plus tan beta 2, that degree of reaction, right? Ca by 2u tan beta 1 plus tan beta 2. What is the value of tan beta 1 plus tan beta 2? It is 2ur by Ca. So now your delta P of rotor, you can get this result 1 by 2 rho Ca square tan beta 1 minus tan beta 2 into this value will be 2ur by Ca. Okay, now if you check delta P static of rotor, how much? It's a half rho Ca square, half rho C you can take inside in bracket tan beta 1 minus tan beta 2, and inside it is 2ur. So Ca square I have taken inside 2ur by Ca. You cut it, ultimately what you will get 1 by 2 rho Ca cancel, so 2 also cancels, so I can remove this part. This 2 and this 2 will be cancelled. Okay. Two and 2 cancel, this Ca and Ca cancel. Okay, this 2 and 2 cancel, so how much you will get? Rest will be the same. So why this is very important, I will tell you. So now rho u Ca r tan beta 1 minus tan beta 2. In one competition they had asked this, not gate, but anytime they can ask. In one day exam it was asked. So what is the question? Simple. This is very important. Okay, so theory question, how In fact, numerical problem also they can make here, no problem. But theory they had asked one time, delta P static of rotor, static temperature rise by rotor is directly proportional to obviously density U CA, but most importantly R. Okay, so I will write this U 0.2 delta P also directly proportional to CA, 0.3 delta P also directly proportional to density, fourth delta P also directly proportional to R. R is the degree of reaction, and fifth is delta P also directly proportional. This tan beta 1 minus tan beta 2. This tan beta 1 minus tan beta 2 in my last lecture when I explained that stage temperature rise, no? Stage temperature rise. Then I told you that time, I said this is called fluid deflection. What it is called? Fluid deflection. More fluid deflection, more pressure rise. These are the parameters. R is the degree of reaction. There should not be any confusion. Last lecture I had explained nicely. Degree of reaction. Okay. I think I should write somewhere here. Degree of reaction R. This formula last class I had derived. So in one day exam they had asked one time. Okay, so the static for the static pressure rise in rotor, basically these are the factors. Okay, if you change U value, if you are increasing U, the rotational speed of the compressor, so static pressure will be more, or static pressure rise will be more in rotor. And in rotor, if it is more, then obviously for the stage it will be more. Similarly, CA. Similarly, degree of reaction. So if you increase degree of reaction, for that reason, for more pressure rise, now you can relate. Last class I had explained, if R is 0, that degree of reaction 0 means there is no rise pressure rise in rotor, and by this formula directly you can get, if R is 0 then delta P will be 0. If you remember last class I had explained, if degree of reaction 0, then what is the mean of it? So you got that impulse turbo machine, right? And that time also you got there is no pressure rise in rotor, and now by this formula also it is proving that statement. You had derived something and you got that statement, check previous lecture. Now here also you can get that same relation. Okay, if R is 0, delta P will be. So this is very important here, and the theory question they are asking, totally we have 5 points and 5 MCQ we can design for this particular formula. Simple. What is the static pressure rise in rotor will be increasing if any option they can select. If U is increasing, U is decreasing, U is constant, there is no effect. Second question, they can make same thing for the degree of reaction. They can ask like static pressure rise by rotor or in rotor. If degree of reaction increasing, degree of reaction decreasing, no effect, none of the above. So any question they can ask, total 5 questions. So for that reason, intentionally I just wanted to explain this formula. I hope this one is clear to you. Okay. So done. Now we have a performance coefficients. Okay, it's called performance parameter. Basically these are coefficients. Okay, coefficients. Now so okay, and these are one by one I will write. These are flow coefficient. It is denoted by phi. Next we have rotor pressure loss coefficient, it is denoted by psi, or another we can psi also we have for loading coefficient. We can write this is the J. Okay, then we have rotor enthalpy loss coefficient, rotor enthalpy loss coefficient, okay, omega. Then we have next stator pressure loss coefficient, and this is denoted by, this was the rotor, so this is zeta stator. Then we have a same thing, a rotor enthalpy, so now we can say stator enthalpy loss coefficient, it is denoted by omega r, so this is omega s. And the last very important, it is called loading coefficient. Actually it is called temperature loss coefficient, but I will write here loading. Loading, this is very important, okay. Loading coefficient, it is denoted by psi. So these are the all coefficients here I have written, I think total 6, no? So these are the, so for all I will explain and I will write formula, that's all, okay. By the word only you can understand here, you know. Obviously if it is pressure, stator pressure loss coefficient, so we will talk about the because it's a coefficient, so it is dimensionless, so whatever the pressure loss divided by dynamic pressure with respect to that quantity. If it is stator, so dynamic pressure in stator. If it is rotor, so dynamic pressure in rotor. That's only, no? Simple formula, but this is very important, okay. All right, so from first we'll start here. So we have first, this is what flow coefficient. So flow coefficient is basically, it is the ratio of axial velocity to rotational speed. Simple. And it is denoted by phi. What is the axial velocity? It is Ca. What is the rotational speed? It is U. So simple, they can ask in exam what is the flow coefficient. So if you know the formula, you can answer for that. Okay. And it is also called compressor velocity ratio, because both are velocity, right? It is also called compressor velocity ratio. This is the number 1. Now we'll go for the number 2. What is the number 2? It is the rotor pressure loss coefficient. Zeta r. So what is the rotor pressure loss? So rotor pressure loss in the sense, in rotor what type of pressure you have? Relative pressure. Yes or no? Just now I had explained, only relative pressure you have. So what is the relative pressure? It is P02 relative in rotor, you had seen. Check You had seen that pressure across the rotor is what? Relative pressure, yes or no? P02 and P01. So now if it is the actual one, so there will be the loss of the pressure, okay? So it is defined as the ratio of pressure loss in rotor due to relative motion of air to the pressure equivalent of relative inlet velocity. So in this case, whatever the P02 minus P01, that is the relative pressure, divided by, because it's a pressure, so because it's a coefficient, so coefficient means dimensionless, so whatever the relative pressure and equivalent dynamic pressure we need to divide, so pressure by pressure becomes dimensionless. So what is the dynamic pressure? It is 1 by 2 rho, and it is nothing but W1 square. Okay, this is the relative pressure. Similarly, third point, this is the pressure loss coefficients. Similarly, we have a third point. So theory I am not writing here because not required. No? The main formula is very important, so you just write it. So what we have, it is called rotor enthalpy loss coefficient. No? So rotor enthalpy loss coefficient, I think it is denoted by omega, right? So omega r. So as the word only you can understand rotor enthalpy loss. So whatever the enthalpy loss across the rotor, okay, across the rotor, and we need to write that enthalpy in denominator. Then one lead enthalpy by enthalpy, it will become dimensionless because coefficient is what? Dimensionless. So we are talking about the enthalpy, rotor enthalpy, okay. So basically it is defined as the ratio of difference between the actual and isentropic static enthalpy, okay, to the enthalpy equivalent of relative inlet velocity. So whatever the enthalpy loss in actual and ideal, so actual, that diagram I had drawn, if you remember, T2 and T2 dash I had shown you many times, HS plot and TS plot. So actual enthalpy rise is what? H2, and ideal or isentropic enthalpy rise is what? H2 dash. So this is the rotor enthalpy loss, and equivalent dynamic enthalpy we need to write, or we can say equivalent of relative inlet velocity. So related inlet velocity will be half into W1. So this is the enthalpy equivalent, half W square, or half into velocity square is the equivalent enthalpy. Okay, equivalent enthalpy. So enthalpy by enthalpy becomes dimensionless, hence it is a coefficient. So we can say H2 minus H2 dash, this is the actual enthalpy and isentropic static enthalpy, and that difference will be the loss. And if you want to write this in terms of temperature also, you can write Cp T2 minus T2 dash, okay, divided by, this is equivalent enthalpy half, because it's a rotor, so you will have a relative velocity. This is the formula, half omega 1 square. Okay, this is the rotor enthalpy loss coefficient. Similarly, we'll go for the next, which is nothing but diffuser, or you can say stator pressure loss. So I think it's the fourth number, stator pressure loss coefficient. Stator pressure loss coefficient, right? So it is nothing but zeta s. So what is the zeta s? It is the stator pressure loss coefficient, just like you have written here rotor pressure loss coefficient. So now you need to write stator pressure loss divided by equivalent dynamic pressure in stator. So what is the value of stator pressure loss? So you can say, one more thing, just I want to correct this. Okay, fine. So stator pressure loss. So in stator, the rotor is what? Between 1 to 2, and stator is what? In 2 to 3. So we have the value, it is P02 This is the stator 2 to 3. This is the stator divided by equivalent dynamic pressure. So in stator, what is the velocity? So half rho, we can say velocity is nothing but c square or ct square. Huh? Why I am writing C2? Because it is the inlet to the stator. C2 is the inlet to the stator velocity, absolute velocity. So this is the stator pressure loss coefficient. So in theory point of view, you can say it is defined as the ratio of pressure loss in stator due to flow velocity to the pressure equivalent of actual inlet velocity to the stator. So pressure equivalent is what? Half rho v square, you heard, it is the dynamic pressure. So this is the pressure equivalent, just like a enthalpy equivalent velocity. Here value you have half w square is what? Enthalpy equivalent. Similarly pressure equivalent, we have quantity, it is called as dynamic pressure. So p naught 2 minus p naught 3, this is the pressure loss in a stator, and equivalent pressure will be the dynamic pressure. So half rho v square, and instead of v you can write c2 square. Why c2? Because c2 is the absolute inlet velocity to the stator. I think this one is clear. So this is the fourth point. Okay, now fifth is nothing but, so we have fifth. What is the fifth point? We check. Fifth is stator enthalpy loss coefficient. Okay, stator enthalpy loss coefficient. Stator this is the stator enthalpy loss coefficient, right? So same thing, in just like you had written for the rotor enthalpy loss, so now you will write enthalpy loss for the stator. So where is the stator? It is between 2 to 3. So actual enthalpy minus sorry, it is the third point. It's the actual enthalpy S3 minus isentropic enthalpy S3 dash divided by equivalent enthalpy. So what is the equivalent enthalpy? It is half rho, not rho, half CT square, just like here. See, this is the half rho W, half W square is the equivalent enthalpy. Okay, this is the equivalent enthalpy. I can write here. This value is what? Equivalent. If you remember, we had written total enthalpy is what? Is static enthalpy plus V square by 2. So this V square by 2 is what? Because you are adding enthalpy in enthalpy, so definitely this is also equivalent enthalpy. So this is called equivalent. Many times you had done this, H naught is equal to H plus V square by 2. So this is what? Equivalent enthalpy. I am just recalling you. Okay, done. Now and if you remember, for the pressure, I just want to write pressure. If you remember, if you write total pressure, so total pressure is what? Is static pressure plus dynamic pressure. What is the dynamic pressure? Half rho V square. So this is what? You are adding this quantity in pressure, so it means this is the pressure. So this is called equivalent pressure, and this equivalent pressure called as dynamic pressure. Yes or no? Right. So stator enthalpy loss coefficient. So actual enthalpy in stator minus static isentropic enthalpy, and this difference will be the loss enthalpy in stator, or you can say diffuser, divided by actual. So it is defined as the ratio of difference between the actual and isentropic enthalpy to the enthalpy equivalent of absolute velocity. So half CT square is the equivalent absolute velocity of flow, and this is also called as equivalent enthalpy. All right, last one, 6 point. So 6 is very important, and they had asked question based on this in one day exam. So this is called loading coefficient. Okay, this is called loading coefficient, or it is also called temperature loss coefficient. Temperature loss coefficient, it is denoted by psi. So what is the psi? So psi is nothing but this is, by the word you can understand that temperature loss coefficient. So loading coefficient also is the ratio. It is defined as the ratio of actual stagnation enthalpy rise in states to enthalpy equivalent of peripheral speed of the rotor. So the actual enthalpy rise across the total enthalpy rise across the stage divided by the enthalpy equivalent in terms of velocity you need to write, but what velocity? It is the speed of rotor. So what is the speed of rotor? Half speed of rotor is nothing but u. So half u square is the equivalent enthalpy. Okay, so in word you can say it is defined as the ratio of the actual stagnation enthalpy rise in stage to enthalpy equivalent of peripheral speed of rotor or equivalent of rotational speed of rotor. So here this is the equivalent equivalent to equivalent of rotational speed of rotor, and this is what? Enthalpy. This is called dynamic enthalpy also sometimes. So delta H naught. So what is the stage enthalpy? So stage enthalpy is nothing but H naught 3 minus H naught 1 divided by half U square. If you remember, H naught 3 minus H naught 1 also, it was input to the compressor. So it is half U square. Okay. So what is the psi? This is very important formula. Psi you got here now. Psi I just want to write because this is very special. So it is sometimes you can understand W input divided by half U square or 2W by U square. Okay, and this is also you can write to H naught 3 minus H naught 1 divided by U square. Okay, so this is the formula, and this is also called as temperature loss coefficient. It is called as temperature loss coefficient. Now if you remember this formula also you can write in this format, 2 by U square. What is the W? If you remember, work input to the compressor I had derived in terms of CA. In terms of CA, I had derived, that is what, that was the work input to the compressor, or it is also given in terms of the CP delta T. If you remember, it is also given in terms of CP delta T. Okay, so work was in terms of both WUCA in terms of beta, just I want to write, so it is tan beta 1 minus tan beta 2. Okay, so if you check, this formula is also U is equal to 2 by UCA tan beta 1 minus tan beta. Okay, so this is the formula. In all aspects I have written, so these are the performance parameters. So anytime the question will be asked to you, so you may be able to answer for this. All right. Now a very special quantity which is the polytropic efficiency. Okay, latest if you check gate question, I think one time they had asked, and this parameter is what very important. Separate I'm just going to explain that 6 parameter what I had explained, it was the coefficients. Okay, now I'm just going to explain this polytropic efficiency. It's very important, no? So polytropic efficiency for compressor. Polytropic efficiency of compressor. So this polytropic efficiency also called as this polytropic efficiency also called as uh, small stage efficiency. What it is called? Small stage is efficiency, and this polytropic efficiency is what denoted by eta p. Okay, so the small stage efficiency or polytropic efficiency is defined as the isentropic efficiency of an elemental stage. Okay, infinitesimal might be you heard. So infinitesimal means elemental stage of the compressor which remains constant throughout the whole process of compression, which remains constant throughout the whole process of compression. So basically if you are going to talk the small stage or the infinitesimal part of the compressor, if you are going to define the efficiency, then it is called as a polytropic efficiency. That's the reason polytropic efficiency also called as a small stage efficiency. It is also called a small stage efficiency. Okay, all right. and in turbomachine might you have derived in during your BTech coursework the sum of isentropic. This was the derivation for 8 marks if you remember in turbomachine subject. The sum of isentropic temperature rise for all the elemental stages is always greater than a single overall isentropic temperature. So this was the derivation if you remember. So we are not going to derive that part. Just I want to give the relation between the polytropic efficiency and isentropic efficiency. That is very important. Okay. So especially you understood might be the small stage efficiency or polytropic efficiency of compressor. The word only you can understand is small stage. So if you are going for the infinitesimal, if like I just want to go for from 4 stages we have. Okay, so if you talk about the small stage, okay, and infinitesimal stage, if you break in infinitesimal stage, so for infinitesimal stage you will talk the polytropic efficiency, but throughout the compressor if you talk then it will be the isentropic efficiency. Yes or no? So polytropic efficiency is the efficiency of compressor stage operating between an infinitesimal pressure differential. Okay, or it is for very small segment. You can say it is for a small segment, or in other word you can say in multi-stage compressor the polytropic efficiency is used in defining the isentropic efficiency of individual stages So most of time this polytropic efficiency basically used for the multi-stage compressor. Okay, it will be used for the multi-stage compressor because we have suppose multi-stage compressor, suppose four stages we have. So that one stage it comes under a small stage, right? It comes under a small stage. So if it is multiple like 6 stages, 7 stages, 8 stages, so among 8 stages for one stage if you talk then it comes under small stages. So small stages efficiency also called polytropic efficiency, or polytropic efficiency also called a small stage efficiency. So hope this one is clear, like, because see this the relation is very important, like if polytropic efficiency is given then how to get isentropic efficiency, or isentropic efficiency is suppose given then how to get the polytropic efficiency. That is main motive to give this data. Okay, so I can write here in multi-stage compressor, the polytropic efficiency, which is eta p, the polytropic efficiency is used in defining the isentropic efficiency eta s, or compressor, so eta c. Eta c is isentropic efficiency. Okay, defining the eta c is the isentropic efficiency of individual stages. Hope you understood why this is always comes in multi stages. So for multi stages compressor, if you want to go for the individual stages, then it will be the polytropic efficiency basically used to define the isentropic efficiency. Okay. Otherwise, that definition I had given, the polytropic efficiency is defined the isentropic efficiency of an elemental stage of the compressor. Okay. The second one also I can write here. So any one you can, because theoretical point of view they can ask the difference also. Okay, the statement wise. So basically polytropic efficiency, which is eta p is defined. Eta p is defined as the isentropic efficiency eta c of an elemental stage, like total 10 stages we have. So one stage will be elemental stage or infinitesimal of the compressor of the, you can, the whole system suppose break in multiple parts, so that for multiple parts, in among that multiple, one segment you take, and that for that you will talk polytropic efficiency. That's the mean of it, of the compressor. Okay, which remains which remains constant, which remains constant throughout throughout the whole process of compression, this is the main meaning of polytropic efficiency. All right, so now the important, this theory is important, it's okay, because one time they had asked about the Bernoulli equation, very nice question they had asked, like it is applicable for the study in compressible and irrotational, and instead of irrotational one they had given inviscid. So if you read 2015 question, then I will solve also. It is very tricky question and very nice question. So sometimes theory question also they may ask, okay, and very nice question they will ask to you. So question they had asked based on eta p and eta c. Okay, so this statement will be very useful for you. Okay, for that reason I have given. Otherwise, this formula is very important. Okay, so how to get the formula? So derivation I will not do, I will give direct formula here, okay, and one graph I will give so you can understand easily. Or graph is required, it is not so much required, but if you want I will give, otherwise this formula is very important. What is the formula? We have eta c, check eta c, okay, eta c is equal to P naught 2 by P naught 1. This is the pressure ratio, P naught 2 by P naught 1, gamma minus 1 by gamma minus 1 divided by, this formula is very useful. Okay, I think latest one question they had asked based on the polytropic efficiency and isentropic efficiency. Exactly, I don't remember, you need to check previous year gate question. Minus 1, this is the formula. Okay, or this one you can write P naught 2 by P naught 1 is RP to power gamma minus 1 by gamma minus 1 divided by RP to power gamma minus 1 by gamma to whole power 1 upon eta. Okay, this is in power, don't get confused, this is in power. This is in power. and then -1. Let me write here, eta c is equal to rp to power gamma -1 by gamma -1 divided by rp to power gamma 1 minus gamma 1 upon eta p minus 1. Eta p minus 1. Okay, so this is very important, and this formula will be very useful for the conversion of eta c and eta p. Let me write, eta c is isentropic efficiency of compressor, eta p is polytropic efficiency, rp is pressure ratio of compressor. If you know this formula, latest gate question they had asked based on this. If you know this formula, within second you can go for the question and you can hit that. Okay, nice. Now, as I told you, the conversion between the this is the conversion of polytropic efficiency into isentropic efficiency. One more conversion you can write, that is called the conversion of index from polytropic index to adiabatic index. That also you need to write. Okay, it is important. So like this is called polytropic index. Okay, so how to write this polytropic? So polytropic index is, now you know, it is denoted by n, and adiabatic index, you know, it is denoted by gamma. No? So that relation I just want to give you. Sometimes it is very useful in numerical. Okay, so if polytropic efficiency is given, and then your relation between gamma minus 1 by gamma into n upon n minus 1. This is the formula you need to remember. Okay, this is the formula you need to remember. So if they have given a polytropic efficiency, okay, so polytropic index you can get, because gamma will be known for air. So this is the formula, eta p, as usual, it is polytropic efficiency. Okay, all right, so done.